All right, today we're jumping into a topic that is quite literally at the core of how we build our modern world. We're talking about the art and science of shaping metal and what it really takes to get that job done right. So let's get into it. You ever stop and think about that? I mean, why is it that some materials just give way? You can sculpt them with amazing ease, while others, like the super alloys inside a jet engine, they're just brutally, stubbornly difficult? Well, the answer to that question comes down to one powerful concept: machinability. And trust me, understanding it is the key to making just about everything you see around you. So here's how we're going to break it down. First, we're going to define what machinability actually means. Then, we'll dig into the three big factors that control it: the material itself, the tool doing the cutting, and the environment of the whole operation. And finally, we'll see how it all comes together in this high-stakes balancing act. Okay, so first things first. When an engineer says a material has good machinability, what are they really talking about? This definition is so important because it's not just about how easy it is to slice through a piece of metal. No, it's this incredibly complex dance between getting a perfect surface finish, hitting dimensions with microscopic precision, making your very expensive tools last as long as possible, and, of course, doing it all without breaking the bank. It really is the ultimate measure of how well a manufacturing process is performing. And how do you measure that performance? Well, you look at these key things. You want low cutting forces, right? So the machine isn't just fighting the material the whole time. You absolutely need your cutting tools to have a long, productive life. You need a flawless surface finish. Think about the smooth metal on your phone. But most of all, you want to keep the temperature down, because as we're about to see, heat is the #1 villain in this whole story. Which brings us to our first major factor. It all starts, not surprisingly, with the material you're actually trying to shape. And this slide really gets to the heart of it. On one side, you've got materials that are pretty cooperative. They tend to be less hard, but their real superpower is high thermal conductivity. They're brilliant at pulling all that destructive heat away from the cutting tool. But then you have the absolute monsters, like nickel superalloys. They're incredibly hard, they stay strong even when they're glowing red hot, but their most villainous trait? It's their low thermal conductivity. They don't get rid of heat, they concentrate it right at the tip of the tool, basically trying to melt the very thing that's trying to cut them. Which, leads us perfectly to our second factor: the tool itself. If the material is the challenge, then the cutting tool is your hero in this fight. So how do we protect our hero? Well, an uncoated tool is just completely exposed to all that insane heat and friction. But with modern tech, we can give it a high-tech suit of armor. In fact, research by Uzlu and his team on tough aerospace alloys found that a ceramic coating, in this case aluminum oxide, acts as a fantastic thermal barrier. It's like a tiny heat shield, keeping the temperature in the chip that's being cut away and not in the tool. And that dramatically reduces wear and tear. But look, no matter how advanced it is, every tool eventually wears out. It's just unavoidable. It all starts with a perfect sharp edge. Pretty soon, friction starts to create flank wear right along the tool's side. And at the same time, the crazy heat and chemical reactions cause crater wear, which literally digs a ditch on the top surface of the tool. Eventually, those two combine, the edge gives way, and the tool fails. The entire game is about slowing that process down as much as humanly possible. And that brings us to the third piece of this puzzle: the environment where all this action is happening. This is where we can actually fight back against those destructive forces like heat and friction. Let me just say this again, because if you remember one thing today, make it this: heat is the ultimate enemy. Every bit of force generates these incredible temperatures right at a microscopic point. So what's our primary defense? Cooling and lubrication. And the impact of a good defense can be absolutely stunning. A 2023 study by Demorpilot looked at machining this really tough mold steel. When they cut it dry, they set a baseline for how fast the tool wore out. But when they used a technique called minimum quantity lubrication, or MQL, which is basically a super precise high-pressure mist of oil, tool wear plummeted by 60%. That is a massive, massive improvement, both for how long the tool lasts and for the environmental impact of the whole process. Okay, so we've met the players, the material, the tool, and the conditions. Now it's time to bring it all together and see how they have to work in perfect harmony.
Because this really is the secret to all of modern manufacturing. You could have the most advanced cutting tool on the planet, but if you pair it with the wrong material or you run it under the wrong conditions, it's going to fail, and fail spectacularly. Real success, the kind that builds the world around us, comes from creating a perfectly balanced system where every single element is optimized to support all the others. And right at the core of that system is this fundamental trade-off. It's a constant push and pull. Every manufacturer wants to make things faster, right? To boost productivity. And you can do that by increasing the cutting speed, the feed rate, or how deep you cut. But as you can see here, every single one of those actions puts more stress, more heat, and more pressure on the tool, which means it wears out faster. So the ultimate challenge is always finding that perfect sweet spot between speed and endurance. So why do we pour so much brain power and so much money into all this? Because getting machining ability right lets us do incredible things. It is how we create stronger, safer jet engine parts from titanium alloys that are almost impossible to cut. It's how we build more efficient cars and life-saving medical implants that are designed to last for decades inside the human body. And when we do it better, it means lower costs for all of us and a smaller environmental footprint for everything that we make. And that leaves us with one final, and I think really critical thought. We are constantly inventing new materials that are lighter, stronger, and more heat-resistant than anything we've ever seen. But with every new composite, every new superalloy, the challenge of actually shaping it gets exponentially harder. So the question isn't if our methods will have to evolve, but how fast they can evolve to keep pace with the materials of tomorrow. That is a race against innovation itself. Thanks for joining us.